Documental offloading is an offloading approach to produce a different transformation of data from mainframe source that already embeds the required business logic to produce the best view for specific business cases. Offloading from the mainframe is a very old and acquired technique to reduce the load on the mainframe, also reducing related costs on the mainframe, and to create separate copies of data that can serve use cases without clogging the mainframe. The difference between traditional offload and documental offload is the way data is replicated outside of the mainframe. In the traditional approach, what we do is create a one-to-one copy of the original schema, which replicates literally the same data available on the mainframe and can be accessed with the very same semantic that can be used on the original schema on the mainframe. In documental offloading, what we do is create JSON documents that represent the same amount of information, the same parameter of information, structured possibly in a hierarchical way, so also highlighting the relations between the entities represented on the original model that can be consumed as a ready-to-use document for different use cases that can access the information they require by consulting the specific section of the JSON document relevant for their needs. We use this approach for a customer in the banking sector in an initiative aimed at drastically reducing the time for granting loans and credit to their final customers by implementing an advanced automation on the decision process. The mainframe, of course, is one of the source of information for this process. In particular, the domain that we addressed with this project was the credit line and collaterals domain. So all the information related to credit lines, connected products, borrowers, collaterals as guarantee for the credit are involved in this use case. The requirement was to feed all the relevant information both on human consultants that use the information from a web interface to interactively respond to clients' questions, perhaps during the evaluation of a credit line request, and by automatic agent, decision agent, that could access those information to algorithmically decide if green light could be granted on a credit line. The traditional approach that the customer was using was represented by a set of REST APIs that were querying the mainframe schema directly and producing a fixed set of information already in JSON format, perhaps even running for tens of seconds in the most complex scenarios. So, for example, in case of a risk group, a group of risk, so when a company is asking for a credit line and that company is part of a larger group and the exposition of the entire group must be carefully evaluated before granting new credit to the specific company that is requesting the credit line. The API on the mainframe has to perform a long time running cycle of queries to not only extract all the information about the company that is requesting the credit line, but all the companies that are connected in the same group of risk. In that case, the API could even respond in like 20 or 30 seconds. And of course, every time the query, the API is interrogated, the whole cycle must be gone through because information in the mainframe can change any second or even any millisecond, and so the API can't in any way cache data to provide better performance, because those data could be already obsolete and provide wrong information to the consultant or the algorithm querying the data, and thus conducted to the wrong decision about the credit line. So what we decided to do is introducing this documental offload approach, which is basically an architecture formed by a CDC. In that case was Golden Gate from Oracle, that was writing all the information about every table in the source schema involved in the offloading to a dedicated topic on Kafka. A separate topic was holding metadata about transactions, so we also could be able to detect the perimeter of each transaction that happened on the mainframe, all the tables involved in the transaction, all the transformation involved in the transaction. And this is very important for architecture to produce coherent output in the end, consistent output in the end. Because of course, if we collect information from different tables to build our JSON document, and we get different version of the tables involved, let's say non-aligned version of the tables involved, we can produce a JSON document which is at different timestamps in time for different section of its content. So what we created is a Flink engine that could consume topics on Kafka, and based on the information provided by the transaction topic, can identify all the transactions that are part, all the transformation that are part of the specific transaction, and produce a JSON document in the end. The Flink job has an internal state that holds information about the state of the mainframe. So whenever a transaction happens on the mainframe, let's say on a single table, and that table is a part of a set of 20, 30, 50 tables that concur to the creation of the JSON document, the Flink engine already has the last produced version of the document and can just update the relevant section of the document, so gaining very good performance in the production. The JSON documents are then output in the end in different formats. We can stream those documents on different Kafka topics, and so enabling streaming consumption of the documents in the end, so producing continuous processing of the produced documents, or can land on a dedicated database. It could be a relational database or a documental database, even better. And we decided to add to the architecture a GraphQL interface to query the model of the documents. The GraphQL interface is very interesting because compared to a REST API where the output in the JSON document is constant, never changing, and perhaps could contain thousands of attributes, while the client that is interrogating the API perhaps need just tens of attributes, and so there is a lot of information going through the wire without any advantage, without any reason. In GraphQL, you can specify exactly the field that you are interested into, and so obtain a smaller document, which is faster to retrieve and also faster to parse in the end. The engine, the Flink engine, is creating the JSON document using JSLT, which is a dedicated library for JSON transformation. And can produce JSON documents according to a dedicated configuration, which is part of the Flink engine. And this is very relevant because whenever a change on a document schema is necessary, or whenever the need for a different kind of document faces, and so a new document type must be produced, all that is required is just changing the JSLT configuration. So the code base still stands still, don't need any modification. And changing the configuration is something that even a business user, or let's say a non-programming user, can perform very easily to change the output produced by the engine. This is very a good improvement in comparison with the REST API approach that the customer were using before, because changing the logic of a REST API involves changing the source code of the API, and also involves a long quality checking cycle before putting the new version into production. Another problem that they had is the proliferation of different versions of the same API, because every time a change was requested, the new version of the API in the end were deployed side by side with previous versions that no one dared to undeploy, because a lot of consumers were still using the old version. With this approach, with the consumption of JSON documents that are produced automatically in response to changes that happen on the mainframe, and with the GraphQL interface for querying those information, that need is completely vanished, because the schema of the document that is produced does not depend on the logic of the engine, but can be embedded in GraphQL query itself. So every client can specify what kind of output expect to receive from the query, and even if the model in the middle changes, the client receives always the same answer, the same reply that it is expecting. So with this approach, we gained a lot of benefits. First of all, of course, we got the benefit that every offloading initiative gets, which is reducing the load on the mainframe, so freeing resources for other use cases on the mainframe, and reducing, of course, the costs of operation of the mainframe by removing load from it. And that's for sure common to every kind of offloading. But being reactive on the changes on the mainframe, let us produce the JSON documents in terms of hundreds of milliseconds. So we have like less than 0.3 second of time between the arrival of the change on the Kafka topic and the production of the updated JSON document. And most important, once the JSON document is produced, and as long as no updates happen on the mainframe, which we would then catch and update the document, the last version of the document can be consumed and retrieved in really in milliseconds, like 10 milliseconds, 20 milliseconds to extract a specific document. So what before required possibly seconds or even tens of seconds and loaded the mainframe quite a lot and created bottlenecks in the consumption phase on right is now being served in tens of milliseconds and does not put any load on the mainframe. And this is really relevant in scenarios like the one of our customer, when not only there is a human interaction on those data, but the customer wants to implement an automatic decision process where getting updated information, of course, but also in an efficient way, so in with very low response times, is crucial to grant the success of the project. Of course, you can't sacrifice data precision when you are automatically taking a decision, because of course you can take the wrong decision and you can't have long times, long querying times. Otherwise, the whole process gets clogged and the performance are so unsatisfying that the whole project gets abandoned in the end. So having both data consistency and accuracy compared to the source and a good level of performance is crucial to embedding this kind of approach in any automated decision process. Our customer in the end reduced the amount for lending more credit to the customers requesting of like under 20 minutes in the complete process, which is quite a great result for a lot of scenarios where private lending is requested for loans, for example, for mortgages, and this increased the volume of opportunities that our customer could intercept and serve, and raised, of course, the satisfaction level of the end user of our customer. And now they are able to evolve this architecture and the set of documents produced even without asking us to intervene, because no change in the code is requested, and just a change in the configuration is all it takes to update the set of documents that gets produced.